Hey guys, I'm Max, and I'm a TA for Fundamentals of Computer Systems. Welcome to our YouTube channel.
Hey, I'm Jillian. I'm another TA for Fundamentals. And in this series, we're looking to review key concepts from lecture, as well as help you guys build problem-solving skills.
Hi, I'm Evan. I'm also a TA, and we are hoping that ultimately this video series will act as an extra resource for you to use when studying. Okay, what's up? So let's talk about XOR gates. So problem number one was essentially asking us to take a truth table for a 3-input XOR gate and show that using the outputs of the truth table, we can simplify to something like this: X XORed with Y, XORed with Z. Okay, so to do that, let's just first talk about what an XOR gate does. So for an XOR gate, if you have an odd number of inputs that are true, the gate will output a 1. So, let's say I had like a 5-input XOR gate. So here's my 5-input XOR gate, and let's say I were to feed in 0, 0, 1, 1, 1. So here I have 3 inputs that are true, and 3 is an odd number. So therefore, since we have an odd number of inputs that are true, the XOR gate will output a 1. And if I were to, get rid of this 1 and change this to a 0, so now I still have 5 inputs, and I have 2 that are true, so 2 is an even number, so therefore the XOR gate would output a 0. We're not dealing with a 5-input XOR gate, thankfully. We just have a 3-input, and we can apply the same logic here, right? So here we have 0 inputs that are true. 0 is an even number, so 0, the output's 0. Here we have 1 input that is true. 1 is an odd number, so the output's 1. Kind of going similarly through. We got this, 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 and this. Okay, so there's our truth table for this gate, this triple input XOR gate. And let's now create the Kmap for this. So kind of translating or like transcribing our truth table to the Kmap, we see this first row, 0, 0, 0, output 0, so 0, 0, 0, this is a 0, 0, 0, 1, this is a 1. And also you can kind of just look at the Kmap and say, here I have 2 inputs that are true, 2 is even, so, this is going to be 0. Just kind of going in a similar manner, we end up with, sorry, this is 0, that was not clear. So we end up with this, and so here we have 1, 0, 1, 0. So this is our Kmap. And so this is kind of what Professor Kim was talking about in lecture, where she said if you have this like diagonal pattern of 1s or like a checkerboard pattern on your Kmap, that normally indicates that you have some sort of XOR behavior with your truth table, and so you can normally simplify to something like with this XOR symbol. So, and that is true in this case. So the Kmap can kind of help you. It's like a nice little rule of thumb. But the Kmap isn't actually like necessary here, just because after you do your Kmap, you can see that all of the groups in the Kmap are only of size 1, which means that we could have just kind of originally taken our midterms and done kind of a sum of products expression in the first place. So essentially, whatever I'm going to get from this Kmap, the sum of products expression, is going to be the same as if I were to have just done it from the midterms. But I do think it was worth making the Kmap just so we can kind of see, this pattern here that indicates the XOR. Anyway, so let's use the Kmap to create our sum of products expression. So here we go. We have x, and we have y naught, z naught, plus we have x naught, y naught, z, plus x, y, z, plus x naught, y, z naught. Okay, so ultimately we want to use this to show we're going to use this to show something like this. But how is that related? Like, I mean, we have to make some simplification here. So let's start out by factoring out a z and a z naught. So z, and if I factor out a z, I end up with x naught, y naught, plus xy, plus z naught times x, y naught, plus x naught, y. Okay, so right away we can see this should look familiar because we know that A XOR with B equals A B naught plus A naught B. And that is the exact same pattern here. So this is essentially just X XOR with Y. So I'm going to make a variable here. I'm going to say Q equals X XOR with Y. Okay. So then we end up with z times x naught, y naught, plus xy, plus z naught times q. Okay, so this is looking better, but we still don't know what to do with this. And so this ends up being equivalent to x NOR. Let me kind of show why that is and how that's going to help us here. So we know from, let me actually kind of erase this Kmap so I can do some work up here. And I will get rid of this too. So we know that A XOR with B equals A B naught plus A naught B. And this is equivalent to A plus B times A naught plus B naught. And you can kind of just check that by distributing this out. We get A naught plus B naught, A plus B, A naught plus B, B naught. And then this just ends up being a 1 and a 1, which cancel because we have these kind of cancel with the OR, and so then we end up with this. So, this is equivalent to that. Okay, cool. So how does that help us though? Well, if we take A plus B times A naught plus B naught, if we take this and we apply De Morgan's to it, so I'm basically just going to knot the entire thing, right? And by knotting an XOR, I do end up with an X NOR. So I'm going to knot this entire thing and then use De Morgan's to say that this is equivalent to A plus B naught plus A naught plus B naught naught. Okay, so now let's use De Morgan's again. And using De Morgan's again, we get A naught B naught plus A naught naught B naught naught, which equals A naught B naught plus AB. Okay, and the way that I got this was just by inverting my XOR expression. So when I inverted my XOR, I ended up with an X NOR, and this is equal to X NOR. So essentially, like A X NOR, that's the symbol for X NOR, with B equals A B plus A naught B naught. And I have that exact same pattern here, right? And I said that Q was the XOR, which means that Q naught is just the X NOR. Okay, so this just equals Z Q naught plus Z naught Q. And then what do you know? We have the same pattern again, the same XOR pattern up here, so this just equals Z XOR with Q. And then I said that Q was equal to, I erased that line, but I said that Q was equal to X XOR Y. Up here, you can kind of see it directly from the substitution. We just plug that in there. So Q is equal to X XOR with Y. And so this equals Z XOR with Y XOR with X, which is exactly what we wanted to get in the first place up here. So we are good to go. And This is essentially showing that this truth table, right, using all this Boolean expression and Kmap and simplification, can ultimately be represented as this triple input XOR gate, like this. So we're feeding in x, y, and z to get this output, which is just x XORed with y XORed with z. And that's kind of what the problem was getting at. And in general too, like, I would not do this every time. It's just a good kind of thing to know. This might be helpful. Just kind of know that is equal to x XORed with y in case this ever comes up again. Then you can just make a quick substitution and just plug in q naught here and q there. So in case that ever comes up in a problem again, then that should be good. Yeah, cool. So hopefully that was helpful.
Hi everyone, this is Jillian, and today I'll be walking you through a fairly typical problem that you may encounter in this class, which is a type of word problem in which we sort of give you a qualitative description of what a circuit should behave or act like, be logically equivalent to, and you're tasked with drawing the equivalent schematic for that circuit. So let's start by reading the problem. A teacher is forming a team for an inter-school competition. There are 4 students enumerated: Alice, Bob, Chris, and David, and they say what respective subjects they're good at. And we were asked to draw a schematic for a circuit whose inputs are 4 wires, 1 for each student, aka Alice, Bob, Chris, and David, whose value indicates whether the student is a member of the proposed team. And what I usually like to do when I'm doing these problems is just quickly kind of draw out graphically what the words are saying. So here I've just drawn the 4 input wires, labeled respectively A, B, C, and D. It's also sometimes helpful to just make sure you understand what the problem is saying or what these inputs mean by going through an example. So if I have, here 0, 1, 0, 1, 0, that means that we're thinking about a team that just consists of Chris. And here the output is true if and only if a team is good at all of the subjects. So here's what we know graphically from this problem, and we just have this kind of black box of circuitry that we need to draw to get from these 4 input wires to a singular output wire. Cool. So there's also a question of, we're trying to figure out what do we do with this information that we're given, and sometimes the format in which we're giving the information is maybe not the most ideal to think around a problem. So at least for me, I think it might be helpful to kind of rewrite information in terms of the subjects that are given here and enumerate who is good, quote unquote, at what. So, just writing math, econ, history, English, and physics, which are the 5 subjects given in the problem, and just going through each of them. So for example, with math, we see that Alice and Bob is good at math, econ, just Alice, and David, history is only Alice, and English is only Chris, and physics is Bob, Chris, and David. So off the bat, you may already notice some sort of pattern or way you might answer this question, but it's totally natural if you don't, and I will go through a systematic way in which you would do this problem if you don't see it, or if you were given a problem that's maybe a little less obvious. So as a check, just to make sure we're all on the same page here, let me just pick out a few rows to go through. Clearly I have difficulty writing these things out in a straight line, but I'm looking at the 3rd row here in which it's 0, 0, 1, 0, which is actually a case that we considered in the beginning. And why is the output 0 here? The output 0 is true. Is true if and only if a given team is good at all subjects. And so this team that we're considering is just Chris, and he's not good at all the subjects. Therefore, the output's 0. Let's consider one more. We have a team that's just Alice and Chris, and I've said the output is 1. And the reason being because Alice and Chris together can cover all of the subjects. So as a check, just to make sure we're all on the same page here, let me just pick out a few rows to go through. Clearly I have difficulty writing these things out in a straight line, but I'm looking at the 3rd row here in which it's 0, 0, 1, 0, which is actually a case that we considered in the beginning. And why is the output 0 here? The output 0 is true. is true if and only if a given team is good at all subjects. And so this team that we're considering is just Chris, and he's not good at all subjects. Therefore, the output's 0. Let's consider one more. We have a team that's just Alice and Chris, and I've said the output is 1. And the reason being because Alice and Chris together can cover all of the subjects. Math, econ, history, English, and physics. Great. So hopefully now, you understand the intuition behind filling out the truth table for this problem, and we can start to look at the Kmap. So I've just filled out the Kmap. I would encourage you to fill it out on your own based on the truth table that you drew and make sure that you can do this properly. It's very important, as I highlighted here, that you label your axes right. The variables that are represented on the axes don't matter as so long as you just translated the respective values correctly from the truth table, but the actual values is in 0, 0, 0, 1, 1, 1, 1, 0 on the axes. That order is important. So this truth table is pretty easy. We just have one maximal covering here, which is just AC. So let's draw the equivalent circuitry for AC. I'll just draw all 4 wires for completeness, A, B, C, D, and we just take A and C and AND them together. One question that arises is, is it okay to not use all the wires? Yes, it is. But that's the kind of complete answer if you do method number 1, and that's something that's intuitive from looking at that information. But let's also think about a different way you might go about solving this problem, which won't result in kind of a minimum number of gates here, right? We just use one AND gate. That was very minimal. But this is one way you might intuit about the problem if the gate efficiency isn't super important, though we do encourage you in this class to always try to minimize your gates. So let's kind of work through this problem backwards. I have 5 conditions that all need to be satisfied, right, for the output to be true. Those 5 conditions are proficiency in the 5 subjects that we listed here. And from the beginning, when we started the problem, we also know that we have 4 input wires, each of which represents a student, right? So our task is, how can we convert the information of the 4 input wires into, what we determined as the 5 input wires into the AND gate here. So we need to look at which student is good at which subjects, because each of those 5 input wires into the AND gate represent a subject. And so very easy case here is with history and English, there's only one student who's proficient at each. So for example, with history, if we have this wire represent history, only student A is proficient at history. And similarly with English, only student C, Chris, is good at English. And so the 2 wires that feed into the AND gate, which represent history and English, will just be the direct inputs from A and C respectively. Now let's think about a little bit of a harder case with the other 3 subjects remaining. Let's think about math first. So we basically just need one person who's good on math for the output to fill that condition for the output, right? And so if I just need one condition, multiple to be true, that's very logically, immediately I'm going to think of an OR gate versus an AND gate in which we would need all conditions to be true. So I can just use an OR gate here or the 2 students who are proficient at math, because I just need one of them on the team for that condition into the ultimate output to be true. So here I'll just OR B and A, because if I have either of those, or better, both of those on the team, then I know that the team is proficient at math. Same logic here for econ and physics. So with econ, exactly the same thing. I will OR the 2 students who are good at it. So that's going to be A and D. And the exact same logic again will hold for physics, and that will be actually 3 students here. So I'll draw a 3 input OR gate with inputs from B, C, and D. And that's it. That's another logically equivalent circuit. You can see that it uses a lot more gates than method 1, which is the truth table to the Kmap. But it represents the same information, and I just wanted you to see two different ways of maybe intuiting about the problem, and particularly with method 2, for you to maybe develop an intuition of translating gates into logic and into different conditions. So I hope that was helpful, and I encourage you to, pause video and work the problem again on your own and see how you do.
Hey everyone, I hope you're doing well. My name is Max and I'm a TA for CSEE 3827 at Columbia. And today I'm going to be walking you through a problem on circuit minimization and just general representations of kind of abstract objects in digital logic. So our task at hand is to design a minimal circuit that takes 4 1-bit inputs corresponding to button presses, and those are labeled up, down, left, or right, and it illuminates the 6-segment display according to which buttons are pressed. So think of this almost like a joystick, right? So you press, say, left, and then it should theoretically illuminate S3 and S5 to correspond to kind of a left arrow. Likewise, for up and down, it will pick either S0 or S2 and also do S4. And you can press any combination of the arrows. So your first thought when it comes to just logic simplification or minimization in general should instantly be truth table. A truth table is how we get Kmaps, and it's how we generally simplify things. It's how we get logical expressions to begin with. So if you see 2 rows have already been provided of the truth table. One is the behavior when you don't press anything, and that's just every bit is set to low. And one is the behavior when you press right. So if you look, when you press right, S1 and S5 are set to high, and S1 and S5 together do make a right arrow. So we're going to walk through the rest of the rows in this truth table. Again, please feel free to pause the video and attempt it yourself, and then listen to me walking through the rows. So the next row is going to be a left press, and if you see, a left press only illuminates S3 and S5. So those are going to be 1s, and everything else will be 0s. The next row corresponds to both left and right. So what's interesting here is that both of these contain 5, right? So left is S3 and S5. And right is S1 and S5. We only need to illuminate S5 once, so we just pass a digital 1, and S3 and S1 also get digital 1s. So if you're familiar with set theory, think of this almost as the union of the 2 presses. Now we have a down press, and if you see down does S2 and S4, again, so we have the arrow shape. We have down and right, so down and right will need to illuminate S2 and S4, but it'll also need to illuminate S1 and S5. So we have 1s there. If we have down and left, that's very similar, but rather than S1, we want S3. And if we have down, left, and right, well, that's everything except for up. So we only want to put a 0 on S0, and we want 1s on everything else. Now, let's just say we only have up. Up is just S0 and S4, as you can see from the diagram. 1's there, 0's everywhere else. If we have up and right, we want S0 and S4, and then also S5 and S1. If we have up and left, and then instead of S1, we want S3, but otherwise it's the same as before. And if we have up, left, and right, well, that's everything except for down, so we want everything except for S2. We're in the home stretch. Now let's say you have up and down. Remember again, both of these have S4, but you want S0 and S2. So S0, S2, and S4. Now let's say you have up, down, and right. So that's everything except for left. So the only one you exclude is S3. If you have up, down, and left, the only one you exclude is S1 because that's right. And then if you're pressing every button at once, I don't know if you have a video game controller or like an Xbox controller. I've tried doing this a million times. I've never succeeded. I'm sure you have too. But in this case, we'll pretend like you can actually do it and you get all 1s because every bit should be set to high. Cool, so that's essentially how you get the truth table from kind of this abstract concept of a real world like digital device. Now, how do you minimize this, right? So your first thought could be to do a Kmap, but that would take a lot of time. And you definitely could do a Kmap for this, but there's actually an easier way, right? So if you look, S3 only lights up when you press left. So S3 is just equal to left. S1, correspondingly, only lights up when you press right. S2 only corresponds to down, and S0 only corresponds to up. Now S5 corresponds to either left or right. And again, we're expressing it here as the sum of products, and the products are just left and right. And then S6 only, there is no S6, it is S4. S4 only corresponds to up and down. So if you see something like this on an exam, your first thought might be, okay, let me make 5 Kmaps or 6 Kmaps. But this is actually much faster if you just think about it at kind of a higher level, and this is really a problem-solving strategy that videos like this are meant to teach. So I hope you enjoyed it, and good luck with the next examples.
This question here asks, using 4 full adders, design a circuit that accepts 7-bit input and outputs the number of input bits that are 1 as a 3-bit binary number. So often you'll be given some sort of combinational circuitry constraint here, which is not necessarily the only way in which you would want to achieve this functionality, but we're imposing this constraint to see if you understand the circuitry, or it might be a more efficient way, most efficient way to go about doing this problem. So let's refresh ourselves on what a full adder can do. We don't need to deal with the internals of this circuit, but takes in two bits here, x plus y, and then plus a carry bit to output one resultant bit is what I call it, and then a carry out bit. So that's what we mean by full adder. It's always important to make sure you understand how that works before you move on. What we're trying to do in this problem is output the number of bits that are 1. So if we have a 7-bit output, let's just label each of the bits here. What we want is the binary version of just adding all these singular bits together, right? So we're just going to be doing basically a 7-bit addition. And we see that each full adder can take in 3 input bits. So naively you might say, okay, well, we need at least 3 full adders here. And the reason you're going to need one more actually to do the circuit is to deal with the carry bits as well, right? So each full adder will only output, 2 bits or 1 bit, and we need the output 3 bits. So we're going to need 4 full adders. So let's think more about what the output's going to look like. With 3 output bits, I'll just label them S2, S1, S0. And basically, these 2 higher order output bits, these are going to be probably influenced by the carry out. And this is just going to be the initial resultant bit of this 3 adder approach that we just talked about. So let's think about why that would be the case and start drawing some circuitry here. So I'm going to need 3 full adders just to get this resultant bit first, and then we can talk about the 2 higher bits. So we can take in 6 bits here, and then we can take in the 7th bit up here. So I'm just going to label this consistently with the final answer key, but addition is associative commutative, so you wouldn't necessarily have to do it in this order per se. But let's think about what this outputs here. So this top full adder is going to output B plus C plus D. This bottom full adder is going to output E plus F plus G. We have some carry outs that we're going to put aside for the moment. Then we're going to feed that into another full adder, which will output A plus great. So this is the bottom resultant bit that we want. This is S0. But we need to deal with all these carry outs that are going to ultimately determine binary equivalent, right? And so we're going to need to use another full adder, one more, to deal with basically the carry outs. So I'm just going to feed in them like so. So let's just say this is, excuse me, this is C out 0, C out 1, C out 2. That's going to be the middle bit, middle significant bit. And then this carry here is going to be the uppermost significant bit. So I hope that explains a bit more about the intuition as to how you might go about solving this problem in a bit of a modular fashion.
Okay, so today we are looking at this problem, which is giving us the same circuit as, I think this was in PSET 3, number 3, but in that problem you were asked to kind of draw the timing diagram for a given input, and here the problem is basically saying, are there any inputs for which a glitch occurs, and if so, which ones, and kind of give an explanation of why the glitch occurs. So, a good formulaic way to find a glitch is by using a Kmap. But to create a Kmap, we're going to have to go through the truth table, and then we can identify disjoint groups in the Kmap. So let's get started doing that. So we're going to check out this first input, 0, 0, 0. And if I feed these into here, we get a 1 going into here. So these are going to flip, going through the inverters. We're going to get 2 1s into this AND gate, which will give us a 1 here. And then I'm going to get, well, to be honest, I don't even care what I'm going to get here, because I know that I have a 1 going into an OR gate, which will give me a 1 on the output. And that's all that really matters, right? So, in general then, looking at the circuit, we can see that the only time that this AND gate is going to give us a 1 is when A and B are both 0, since we're flipping them and then feeding them into this AND gate. So that means that for these first 2 rows, I know that the output is going to be 1, since A and B are both 0. So 1 and 1. And then for all of these remaining rows, I know that A and B are going to give me 0 here, because really this is not A, not B. And if I look at all of these values, this is all going to be 0, which means that we're going to get a 0 in here. And so that means that I'm really only focused on B and C for the remainder of the truth table. So okay, then I'm looking at B and C, and I see that what is important about that is this AND gate is B, C. And so the output of this gets fed into here. So really then I know that this is going to output 1 whenever BC is 1. Okay, so then looking at the truth table, I can see, well, 1 and 0 is 0. 1 and 1 is 1. 0 and 0 is 0. 0, 0, and 1. Okay, so now our truth table is done, and we have to make a Kmap. So let me make this Kmap then over here. So we're going to have A, B, C. Okay, and then then kind of just translating from the truth table to the Kmap, which we did in problem 1. This is going to be 1, this is going to be 1, it's going to be 1, this is going to be 0, this is going to be 0, 0, 1, and 0. And so looking at this, we can see right away that we have these two groups here and here. So we have these two disjoint groups. And so what that means is that there's a possibility of a glitch somewhere, jumping between this group and this group. So we can either have B is falling or B is rising. And so we can kind of test both of those possibilities with the circuit and, using the delay of these inverters, basically, see which one of these, if any, causes a glitch. So, okay, let's start with B falling. Okay, so here, we're looking at this thing. So we have A equals 0, B equals 1, and C equals 1. And then we're going to go to A equals 0, B equals 0, C equals 1. Right, because when I move from here to here, I'm just flipping B from 1 to 0. So let's kind of just see then what our starting state would be, starting at A equals 0, B equals 1, and C equals 1. So 0, 1, and 1. So this is going to become a 1, this is going to become a 0, the final output is going to be a 0 here, and then, or not the final output, but this input into the OR gate is going to be a 0, and then I have 1, and I have 1, and so 1 and 1 is 1, which means that this is a 1, and our final output is a 1. Okay, so that's fine, that's the initial state. And then we need to say, starting from this initial state, when B falls from 1 to 0, what happens? So the first thing that happens when B changes from 1 to 0, so this is becoming a 0, the very first thing that's going to happen is the values here are going to update. So the value coming out of this AND gate is going to update before the value coming out of this AND gate updates. And the reason for that is because these inverters create, there's a delay associated with them. So essentially, these inputs are going to reach this AND gate after these inputs reach this AND gate, which means that the output of this is going to be updated before the output of this. So when I change this to a 0 and a 1, the very first thing that's going to happen is 0, 1, okay, we're feeding that in, and then this changes to a 0, which means that this input to the OR gate changes to a 0, so our output is 0. Okay, so now our output is 0, and then very shortly after, our output is going to update because we now have 0 and 0 here. So this is going to become a 1, and this is going to become a 1, which is going to become a 1. And now our output is going to change from 0 to 1. Okay, and that's our final output. But the important part there was that due to this delay associated with NOT gates, which cause a delay here, which ultimately causes a delay on the output of this AND gate, which then another ultimately caused a delay on the output of this OR gate. We saw that there was a delay on the final output because we started with a 1 and then we wanted to end up with a 1, right? Because here we had a 1 and here we had a 1. But we basically went from 1 and then we had a 0 for a very short amount of time and then we went back to 1. So this incorrect output, that is your glitch. And that means that when we're starting here and B drops, we get this glitch, which means that the circuit has a glitch. And then just for the heck of it too, we can also kind of do the opposite. So if B were to rise, then you would start out with this, and so I guess this will all be the same because we're starting out with B at 0. So this is 0, this is 0, this is 1, this is 1, yep, okay. So this is what our circuit would look like starting out if we were starting out right here. And then what happens when B rises? So when B changes to a 1, remember all these are going to update first since this output value of this AND gate is going to output before the output value of this one. So I'm going to say, okay, I have 1 and I have 1. So that's going to give me an output of 1. And this is going to be 1. Okay, so our final output is still 1. Nothing changes there. And then let's see what kind of happened here. This is going to become a 0, which means that this is a 0, which means that this is a 0. And that doesn't matter because our final output is still going to be a 1. So, we kind of went from 1 to 1 to 1. So, like, even though there was ultimately a delay with the output of this OR gate and with the output of this AND gate, it doesn't matter because this didn't change. So, like, our final output, if you were just like some person looking at the output of the circuit, all you would have seen was that, you went from 1 to 1, and so nothing changed. So, like, the main thing behind a glitch is that, at the end of the day, after you wait the propagation time or however long you need to wait for the output to finalize, the circuit's going to be correct, right? Like, the circuit's not going to be incorrect for any reason, but with a glitch, there's going to be a small amount of time where you do see an incorrect output, which you would not expect from the truth table if you were just only focusing on the output of the circuit. So yeah. Anyway, so the answer to this problem is that when B drops from 1 to 0, in this setup, when you have A equals 0, B equals 1, C equals 1, this drops, you end up with a glitch because you have this small amount of 0 for this small amount of time where the output is a 0. So yeah, hope that helped.